Okay, so last time we reached to example 8, which is about rotational vibration. So we started with the torsional vibration, and then we moved to energy method. And there are two ways in energy method, either to find the equation of motion uh, by applying the conservation of energy, and we use d by dt of the total energy to be 0. Or we use the Tmax equal to Umax to find the natural frequency right away. And example 7, we did that. Okay, and we can, here the question is to find the differential equation of motion. Okay, which is the equation of motion.
دكتور
Yeah, no
ما
sharing.
نشوف السكرين.
Okay. Okay, so this was the example we did last time, but we didn't finish it. The question is about a cylinder rolling over a cylindrical surface. So the first thing I did is to work on the kinematics of the cylinder in this case. I just gave you, we recall what we did before on or a rolling motion of a cylinder on a horizontal surface. Okay, and if there is no slipping, then the angular motion is theta, and the relationship between the horizontal motion of the center of gravity and theta is x equal to r theta. And we will do the same thing similarly, the same procedure we did here is we are going to apply it on this cylinder, which is on rolling on a cylindrical surface with a radius capital R. So the amount of rotation or the angular displacement of the cylinder is measured always with the vertical center line. And I put a reference mark shown here in the green arrow when it is at equilibrium position. Okay, this is the equilibrium position here, the center line. Okay, this is the equilibrium position for the cylinder. And the reference mark is shown by the arrow, the green arrow. When at an arbitrary position, we need to measure the angle made by the reference mark, which is shown by the green arrow, and the vertical center line again. That will be the rotation or the angular displacement of the cylinder. Okay, but we know that we can define theta and we can define phi. The theta is the angle of the sector along the cylindrical surface from this point number 1 to point number 2, which are the contact points of the cylinder with the surface. So this is the bigger sector, the blue, shown with the blue color. Okay, and also there is another sector on the cylinder, which is from the contact point to the reference mark. Okay, and then there is an angle phi. For no slipping, the arc length of the two sectors should be the same, which is capital R phi, capital R theta should equal to small r times phi, which is, we did it somewhere, yeah, this one. Okay, so the arc length in each sector should equal. So R phi, which is on the cylinder, this is the arc length of the sector on the cylinder, should equal to R theta, which is the arc length of the sector in the cylindrical surface. So this is true for no slipping, and then the angle of rotation will be phi minus theta, or the angular displacement is phi minus theta. And using everything in terms of theta, you can change this to theta. You know, you can use the relationship here. You can find angular displacement in terms of theta only. And the same thing with the angular velocity is only differentiating angular displacement with time. It is the rate of change of angular displacement. That is the angular velocity. So it is phi dot minus theta. And I think we call it in the slide, it is called omega, which is the angular velocity. And we can proceed to substitute for one variable. There are two variables here, two coordinates, right? Theta and phi. And those are dependent. And we need to put just one in terms of the other one. So we will put the substitute for phi in terms of theta. Okay, so this will lead to that phi equal to r, capital R over small r multiplied by theta. So we can substitute for phi dot because you can differentiate this equation. Okay, so it is also that phi dot equal to r over small r theta dot. And this will be r over small r minus 1 all multiplied by theta dot. And this is the angular velocity. Okay, so this is the kinematics of the cylinder. One more thing is the velocity, since the type of motion of the cylinder is rolling type, which means it is general plane motion. Okay, general plane motion. The kinetic energy will be due to translation and due to rotation, as you did in dynamics. So here we have, we need to find the velocity of the center of gravity of the cylinder as well. So now we find the angular velocity, and then from this we can find the kinetic energy due to rotation, and we need to find the linear velocity of the center of gravity of the cylinder in order to find the kinetic energy due to translation. The center of gravity is this point, okay, and it is like it is moving in a circle, right? A circle of radius capital R minus small r, right? This is the circle, the radius of the circle that the center of gravity is moving along. And the velocity is always tangent to this, which is perpendicular to the arm. This is the velocity of the cylinder, which is perpendicular to the arm. Now the arm is the radius, r minus r. So this is the linear velocity. It is multiplied by the angular velocity of this line, of the arm. Okay, that we imagine this is like a pendulum. So the angular velocity is theta dot of this line. Multiplied by the distance, it's going to give us the linear velocity. Okay, so VC is equal to R minus R times theta dot. And then this will enable us to find the kinetic energy in rotation and translation. Okay, so VC is the velocity of the center of the cylinder, which is R minus R times theta dot. Okay, and omega is R over R minus 1 theta dot. So everything in terms of theta dot, and then we can apply the kinetic energy. It is a two-part, translation and rotation. The first term here, T equal to 1 over 2 mVC squared, is the translational, due to translation, plus 1 over 2 J C omega. This is, there is no omega dot here, just omega. Omega square. Okay, that's omega is the angular velocity. And now regarding the parameters we have in the given in the question, we have the weight is given, okay, and the radius of the cylinder. There is no m, so W equal to mg, and then we should use W because W is given, that is m equal to W over g. So in terms of the given parameters, the mass is W over g. And VC square is R minus R theta dot all squared plus W over G R square over 2. Okay, the cylinder or a disk, I think we talked about this before, that the moment of inertia is half mr squared. And since we don't have the mass, we have the weight, we have W over G, which is the mass, times R square over 2, times the angular velocity square, which is R over R, minus 1 theta dot all squared. And you can simplify this, okay, which is 3 over 4 W over G R minus a small r squared theta dot squared. Okay, after simplifying, where JC equal to mr square over 2 for the cylinder equal to W over G times R square over 2. This is true, or this is the equation for the moment of inertia for cylinder. And also for a uniform disk in rotation. Now, regarding the potential energy, we don't have a spring here, so there will be only the work and potential energy of due to the weight, due to gravity. We need, in this case, we need to take a data. Okay, it depends of, and then you take the change in work is the potential energy. So if you take the datum is at the center of at the equilibrium position, this is the datum. Which is the line that goes through the center of horizontal line that goes through the center of gravity. So the potential energy here is 0. Work is change in potential energy, right? So we have 0 potential energy here, and then this is the height. This is y. Okay, if we find y, then it will be U is the potential energy equal to mg times y, and mg is W times y. Okay, so it is potential energy is W times y. So we need to find y from the shape here. The distance from here to the datum is r minus r. And then we continue, take a straight line to form a right angle triangle. And then we can find this side of the triangle, and then subtract, we get y. So this is the hypotenuse of this triangle is r minus r, and then the adjacent side is r times r minus r cosine theta. So this is r minus r multiplied by cosine theta. And then y becomes r minus r minus r minus r cosine theta. So we have the potential energy is W times Y equal to W, and Y is r minus r minus r minus r cosine theta. Okay, so you can take r minus r common. And this will be 1 minus cosine theta. Okay, we don't do the approximation from here that cosine theta is small, and I mean sine theta is small and cosine theta is 1, then this will be 0, always 0. Okay, so we keep the approximation to the last steps. Okay, so this is the potential energy. And then to get the equation of motion, we use the rate of change of the total energy is 0. Okay, so we substitute for the kinetic energy and the potential energy. We have d by dt of t plus u equal to d by dt of, we substitute for the kinetic energy, which is a 3/4 w over g r minus r squared theta dot squared plus w, which is the potential energy, r minus r 1 minus cosine theta, and this should equal to 0. And then we carry out the derivative. We have 3/4 w over g r minus r squared, and the derivative of theta dot is 2 theta dot theta double dot plus w, and this is r minus r, and the derivative of 1 is 0, and derivative of cosine theta is minus, and there is a minus, becomes a plus. So this is sine theta times theta dot, okay, equal to 0, as we say. We can simplify. There is 2 here, we'll cancel, this becomes, instead of 4, becomes 2. And you can take theta dot common. Okay, you can divide by w, because this is not 0, and then multiply by g throughout. Or just keep it as it is. So it will be 3/4, I mean 3/2 over g, r, also r minus r will cancel. One of, this bracket will cancel out. So it will be r minus r multiplied by theta dot plus sine theta only. And all this is multiplied by theta dot. And so as you can see, the energy method will give you theta dot as well. So either theta dot is 0 or the bracket is 0. So theta dot is 0, it means there is no vibration. And our equation, or required equation, will be 3/2g r minus r theta double dot plus sine theta equal to 0. This is the differential equation. We put in standard for the theta double dot coefficient is 1. And this will be 2g over 3 r minus r sine theta. And as you can see, this is the nonlinear differential equation. Okay, because of the nature of the problem, which contains, like, since this is the cylindrical surface, so it is part of it is like a pendulum. And now we start the approximation for theta very much less than 1. We have theta, sine theta is, we take it as theta. And it's become linear equation. This is nonlinear differential equation, or equation of motion. Okay, so with the approximation, we get theta double dot plus 2g over 3r minus r theta equal to 0, which is the final equation, linearized. And once we reach to this equation, we know what is omega n, right? the nature frequency is equal to the square root of the coefficient of theta. It is 2g divided by 3 r minus r. Okay, so here is the natural frequency. And always by inspection, huh? Without solving differential equation, it is the coefficient of theta is the, is the way we can find the nature frequency. Okay, I think the next section is about a different topic, so I will start with the tutorial. Okay, tutorial 7 is about free vibration of rotational system. Tutorial 2 was about translational system. Here, question number 1, a flywheel. Now just recall what we did in rotational or torsional vibration. In torsional vibration, the model that we studied was a shaft carrying a disk, a uniform disk, and then the nature frequency is square root of kt over j. But if it is something else, then we have to work on the equation of motion. Okay, so here question 1, a flywheel weighing 70 pounds was allowed to swing as a pendulum about a knife edge at the inner side of the rim, as shown below. If the measured period of oscillation was 1.22 seconds, determine the moment of inertia of the flywheel about its geometric axis. Its geometric axis. The flywheel is and its center of gravity is in the middle. It's like the centroid, but it is not pivoted about the center about the centroid. If it is pivoted about the centroid, it will not oscillate. It can only rotate. But here, in order to find the moment of inertia, you have to support it somewhere at other point. As you can see, it is in the inner side of the rim. Okay, this is hollow here. Okay, this is hollow from here. It is hollow, and this is hollow, hollow, and hollow. So you can put the wheel on a knife edge, and then allow it to oscillate. This is the equilibrium position. If you draw the center line, this is the equilibrium position. Yeah, obvious, right? But that is the equilibrium. And then if it is for balance, this is balance, and the center of gravity will be along this center line. You need, in order to get the equation of motion, you need to draw this shape again at an arbitrary position, let's say at an angle theta. But it will be two figures on the top of each other. So it's I'm going only to draw the center line. So imagine that the whole thing is rotating. So the center of gravity is moving to this point, let's say. So here is the weight, the value. The distance from the center of gravity to the pivot is 12 inches divided by 2. There is 16 inches is the outer diameter of the rim, and we don't need to use it. So we need only the 12. So this distance is I'm going to call it D, and D equal to 6 inches. Then this point, the pivot, let's say it is P. Then you can apply Newton's second law, which is sum of moment about P equal to J P theta double dot. Theta is clockwise. Then if the moment is counterclockwise, then it is negative. We have the perpendicular distance is this. And this is the angle theta. So the perpendicular distance is the opposite side to theta. So it's going to be minus W times D sine theta equal to JP theta double dot. And moving everything on one side, we get JP theta double dot plus W times D sine theta equal to 0. This is the nonlinear equation. For theta very much less than 1, we can use sine theta as theta. And then this becomes JP theta double dot plus WD theta equal to 0, or when you divide by JP, this becomes W theta double dot plus WD over JP theta equal to 0. So what is the frequency of oscillation? The circular frequency is omega n equal to square root of WD over JP. Square root of WD over JP, which is equal to 2 pi over tau n. Tau n is measured. If the measured period of oscillation of the figure shown here, which is the wheel supported on the knife edge at point P, the period of oscillation is found to be 1.22 seconds. So omega n can be calculated from tau n. Tau n is measured. This will be tau 2 pi over 1.22. The weight is given 70. The D is given as 6. You can square both sides and get that WD over JP equal to 2 pi over 1.22 squared. Okay, and this is we have JP becomes equal to 1.22 over 2 pi squared times WD. Okay, so this would be 1.22 divided by 2 pi squared, multiplied by 70, multiplied by 6. And the unit will be pound inch squared. But this is not the required moment of inertia. The question is determine the moment of inertia of the flywheel about its geometric axis. Okay, let's say that is the point O, the center of gravity, the geometric axis. So it is required to find JO, not JP. So how do we find JO? We cannot find it. We cannot find JO directly because the system is oscillating about point P, not about point O. So the moment of inertia we will get is about point P of the same wheel. You know, the wheel has moment of inertia at a different point is different. So at point P it is, you know, this value. Okay, which is try to calculate this.
15.83.
15.83. 83. Okay, pound inch square. Okay, so this is not the one that's required. We need to use the parallax theorem. In order to find JO. So JP equal to JO, always written this way, plus m times the distance squared. Okay. M times d squared. What is d? Usually they use a small letter. D is the distance between the points. Points P and O, which is 6. So JO becomes JP minus M times D squared. So this is 15.83 minus minus the mass. The mass is W over G, so it is 70 over G. G is, we need to calculate G in inch per second squared. Okay, it is 386.4, I think, times 6 squared. Okay, and you can find JO. It is given in the answer as 9.3. Okay, this is pound inch second squared. Yeah, because of the here there's different units. Question number 2 is similar. We have just a connecting rod. Instead of the wheel, we have a connecting rod and supported at the connecting rod will be joining bearings here with smaller diameter and then a bigger diameter. So if it is supported at this point P, a connecting rod weighing 21.37 Newton oscillates 53 times in 1 minute. So this is the observation. When suspended as shown, determine its moment of inertia about its center of gravity, which is located 0.254 meter from the point of the support. Okay, so the distance here is given 0.254 from the pivot to the center of gravity. So if you call this point O, then the question is to find JCG or JO. You do the same thing, you draw the center line at an arbitrary position and then you apply Newton's second law. For question number 3, so it's similar to question number 1. Question number 3, a cylinder of mass M and a mass moment of inertia JO is free to roll without slipping, but is restrained by the spring K as shown below. Determine the nature frequency of oscillation. In example 8, that there was a cylinder but on a cylindrical surface, so it will oscillate about the equilibrium position, which is the minimum point. Here it is on a flat surface, but what makes it oscillate, what makes the cylinder oscillate is the spring. Okay, this will makes the cylinder to oscillate, and it's providing a force. There are either you can use energy method or you can use the Newton's second law. The type of motion, assuming there is no slipping. So we have theta is given here, but as you know that in rolling motion we also need the translational part, which is in terms of x. So for no slipping we have x equal to r theta, although it is not given, but you know that without slipping. So this is the condition for no slipping. Okay, you recall this from dynamics, right? So either you find the equation of motion first. The question is to determine nature frequency. So you can find the nature frequency directly by using Tmax equal to Umax. Okay, so in order to find nature frequency right away, then you can use Tmax equal to Umax. So what is the kinetic energy for the, then we will find the maximum kinetic energy. The kinetic energy for the cylinder is half m x dot squared plus half Jo theta dot squared. You just need to replace x in terms of theta. This will be 1 over 2 m x dot, it means r theta dot all squared plus half Jo theta dot square, and you can simplify this as 1 over 2 and then this is m r square plus Jo multiplied by theta dot square. And then the potential energy U is only the strain energy of the spring because the cylinder is flat or rolling on a horizontal surface. So there is no change in potential energy due to gravity. It is half k x squared, and again you need to replace. You cannot work with two different variables or coordinates. You just one coordinate here because the system is single degree of freedom system. Okay, which is half k r squared theta squared. Now you can use Tmax equal to Umax. So what makes the kinetic energy maximum, as you can see from the kinetic energy expression, is only when theta dot is maximum. So this will be a Tmax equal to Umax. The kinetic energy is maximum is when theta dot is maximum. So the rest of the terms will be the same. Half m r squared plus Jo times theta dot maximum. Okay, this is the maximum angular velocity of the cylinder, equal to 1 over 2 k r squared theta maximum square, which is the maximum angular displacement. And for harmonic motion, we know the relationship between theta dot maximum and theta maximum. This is omega n theta maximum. So you will have, you can cancel 1 over 2, 1 over 2, and then this will be m r squared plus Jo omega n squared equal to k r squared. Okay, because when you substitute for theta dot maximum equal to omega n theta maximum, then you will have a theta maximum will cancel out, and then you have only omega n squared. So therefore, omega n is equal to the square root of k r squared divided by m r squared plus Jo. This is the energy method approach, and you can see this is more straightforward. You can alternatively use Newton's second law. Okay, I want you to think with me with the Newton's second law. The free body diagram is essential, right? Whenever you do the Newton's second law. So let's say, as shown, that theta is positive counterclockwise. So what are the forces we have here? I know that there is the weight, and there is normal force. Okay, those things I know, and you know. What are the other forces? The spring force, right? The spring force is to the right. The reason is that with the assumption theta counterclockwise, the spring will be under tension. So it is pulling the cylinder to the right with force kx. Okay, and we say there is no slipping. Is there is a friction or there is no friction when there is no slipping? Okay, no slipping. How about the friction force? No suggestion.
دكتور static friction.
You have there. The question is, I know the question I just asked you is that there is a friction force or there is no friction force. We will talk about the type of the friction force.
Yes, there is friction.
Yeah, there is a friction force, and as you know that the friction force is either the static friction force, which is the maximum, or a friction force that is less than that, or it is kinetic friction force. For no slipping, of course, this is not the kinetic friction force, right? Because if K is equal to mu K times the normal force, and this is not the case, this is for motion during slipping. This is during slipping. Okay, and there is the maximum, we call it static friction force, which is equal to mu S times N and this is for about the slip, right? Maximum friction force. When the cylinder is about to slip. Okay, so the friction force in general is just F for this case. Okay, it might be the maximum friction force, but for sure it is not the kinetic. But we don't know now whether it is in the no motion, right? Or it might be in bending motion, but that one is jumping to a conclusion without any justification. So it is just a friction. We have to just add it on the free body diagram. So the friction force is always opposite to, you can put it this way, F opposite to the rotation. The rotation is counterclockwise. This will give an opposite friction force F, but it is unknown. Okay, it is not equal to Fk or Fs, which is just unknown, and it is the friction force that for no slipping, this is the force that we experience when you walk on the ground, on the floor. Okay, you don't slip because there is friction, but not equal to the maximum friction force or equal to the kinetic, only for slipping. So just keep the force there, because if you don't put the force, you will have unbalanced equation. Okay, so the Newton's second law is either okay, this is the center of gravity, right? And this is the contact point C. So and you know that the Newton's second law is either sum of forces or sum of moment. This is equal to m x double dot, and this is equal to j theta double dot. The first equation is the sum of forces equal to mx double dot in the x-axis. Okay, with sum of moment equal to j theta double dot, there is plenty of them. You can have just change the point. Okay, let's call this as O. So if you choose O, then this will be sum of moment about O equal to JO theta double dot. Or you can choose point C. This will be sum of moment about point C equal to J. Okay, so if you take moment about point C, it will be JC theta double dot. So for the moment equation, you can have a number of equations, or you can select the one that can give you the answer directly if you want. So if you choose J moment about C, then you take moment about C should equal to JC theta double dot. Now what is given in the question is JO, about point O, not JC. So if you want to find JC, you can use the parallax theorem to find JC. Okay. Okay, we'll come back to this next time. And we'll move to maybe lecture 8. Okay, any questions? All right. Next week, we will have a quiz. And I don't know if I told you or not. We can have a quiz next week on Tuesday or Thursday. Tuesday is 8th of March. If you have no conflict with other subject, we can go ahead with Tuesday. And it's going to be about tutorial 2 only. Okay, so just maybe Tuesday or Thursday, I will see the other section. Yeah, be